idea, like if someone asks you what is machine learning for you?
Okay, I haven't thought about it.
Uh-huh.
I think it's intelligent machine, so usually you can use it for classification and
Yes, so that is what we were discussing, that machine learning is the study to develop a set of algorithms or models which would try to find out the hidden function which will map the input data to some output. Normally, these kind of problems you cannot model it mathematically. Like for example, if I want to make a model which should recognize all of us, so how can I write it? What's the model of Fahad? I don't know. What's the model of Farhad?
You should came up with a
Yes.
model. Just,
So
I don't know.
So for example, the one thing would be that my height. No, but there are like hell lot of guys with this height. My weight. No. My eyes. I have 2 eyes. Everyone has 2 eyes. So what we do then? We try to find out some discriminative features, some data on the basis of which you can really discriminate something. And now I will start giving you some examples. Let's think of something. So okay, so how many tables and chairs you have seen in your whole life?
Infinity.
Not infinity.
Thousands.
Thousands. Hundreds, right? Hundreds of thousands.
Hundreds or maybe.
But in your life, if you see any table or any chair, your mind can directly tell that, okay, hey man, it's a chair. You have never seen all the possible chairs, shapes, and the table shapes in your life, but you have seen like limited versions of this, and your mind captured the function of this table and chair. That okay, you see something, I show you something, and you will say, yeah, okay, this is a chair, it's a table. But if I say that okay, I can discriminate this on the basis of just the legs, no, chair has 4 legs as well sometimes. So you see, so there is something that is really discriminating this. For humans, it's very easy job, but when it's the time to teach this ability to machine, it's hard. So now we'll think, okay, why we need machine learning? We already explained, right? That you cannot find the hidden function. You want to map some input data to output data, and you let the machine learn by experience and let it learn the hidden function itself. Now, what are different terminologies used in machine learning? What are different, let's say, words or phrases that you are like listening to it every day, but you think that, okay, what the hell is this?
Dataset features,
Dataset features,
parameters,
classification, parameters,
regression,
clustering,
clustering,
cross-validation,
Neurons, I don't know.
epoch,
Classes,
deep learning, neural networks,
descent,
capsules.
gradient descent.
gradient
Lee, what comes in your mind? Like, what are the
You
terms
got
that
everything.
you think like, okay, the first one is feature vector, let's say, or data set. You see? So what is feature vector?
is the input vector.
Yeah.
Well, it's a set of descriptions that can describe an observation which we know the answer for. That.
Yes. And the answer is label.
Yeah.
So I will explain now technically. So this one instance mean one example. So let's say this is chair. So this is one instance, one chair. Okay? And I have features of this. So feature can be color, size, some shape. These are the features. And then we assign it a label. And the label is chair. And one chair is one instance. So one instance, feature vector, and label, they are like the basic components of machine learning. Yes? Let's give a better example. Can you come up with something nice, like where we can find the feature vector of something?
For example, my work, we are working on a cell. A cell has like viscosity, density, things.
We'll come to that in the, let's say,
It's hard.
apple and banana.
Those are two instances.
So
Label.
apple is label
Okay.
and banana is another label. In machine learning, normally we always play with numbers. So I will call apple 1 and banana 0. So, and let's say this define color.
Represent their shape very well.
This is shape. What should be
Weight.
weight, yeah.
color.
Taste.
Did you have color?
Taste, let's say we don't know if what's the taste, color, shape, this taste. What's going to be the third one?
Season.
Volume.
No, something relevant to the fruit.
Firmness.
What?
Volume.
Volume, let's say, okay. Volume. And for example, we get these things in numbers. So let's say that the color is 1.5, 1.5 may be representing like little bit of red.
Yeah.
The shape is like circular, and let's say the circular is represented by some number as well. So
We give
3.5, 1.1, 6.5, 7.4. And now these are coming from one example. So we have one apple, and we measure all these values for this, and we call it as 1.
And what's the separate box? That one.
This one is label.
That's actually the objectives. You are
Ah,
trying
yeah.
to distinguish between these ones.
Yes, so this is label, and what is this? Feature
Features.
vector. So now the point is how many features you have? 1, 2, 3, 4, 5. So it's a 5-dimensional feature vector.
5-dimensional.
5-dimensional feature vector. I will explain how you can think in dimensions then. But let's say that we have another like instance. This is also 1. Some other numbers 1.6, 1.3, 3.5, 7.5, 4.7 something, it's also 1. This one thing will be called one instance. This is the feature vector for that instance, and this is the label for that instance. In the same, we will have some numbers for banana and apple. Now, can you think of this as plotting this in some feature space?
Yes, maybe we
Yes.
put.
Imagine that normally in feature, when you're doing like this feature extraction and things like that, it's possible that you have redundant features.
We should eliminate them. Or
Yes,
maybe-
so for example, what can be the redundant feature here? Let's say,
The taste.
Because you
The
have
taste.
shape, so
let's say the weight, because maybe the banana and the apple, they are like of similar weight. Should we ignore this?
I thought the algorithm,
is it gonna count as redundant?
like internally,
If they're
you
the
will.
same.
Yes, because it's not giving you any discriminative power.
No,
Yes, but I think redundant means something that
Extra.
the two features are giving you the same information. For example, you have volume and you have shape.
Okay, I will explain. I will explain. So let's say we want to identify gender of a human.
Okay.
Okay. So they say that with the weight and only the height. No, you cannot do this. But then there were some guys who did this something by combining the weight and thing. So that's another story, that you can combine like two feature and come up with something new feature, and then it may be good. But let's say, like as we mentioned for the chair and table, if I have only one feature, that the number of legs, can it give me any information about things? Like if I tell you that, okay,
No, probably not.
no. If I tell you both, that okay, the number of legs and the surface area,
Yes.
still the number of legs is redundant, irrelevant.
I have a question.
Yes.
I thought we should only put discriminative features. So we don't talk like.
And that's the point.
So we should like eliminate all the.
Yes, the redundant features.
Yeah.
And there are techniques like you use sometimes PCA. Yes, yes. And that's the point. But I wanted to remove some redundant features because I wanted to plot something. Let's say we have only 2 dimensions. Like, let's say that even volume is redundant here. This is also redundant. So let's say we have color and shape. And when we plot something, it's possible that the label 1s will come here, for example, and the label 0 will come here. Now this is in two-dimensional space.
Yeah.
You can think of this
Yeah,
as a
Those
3D as
two
well. So if you have
dimensions, I
3,
think are the color and the
shape.
shape. Yeah, so this point, like label 1, it has 1.5 on x-axis and 3.5 on y-axis. And you plot it here. Then you have another one, you plot it here. You have another one, let's say this, we have ones. 1, 1, 1. You plot it here. So this is one instance. So this one instance corresponds to that. If it's two-dimensional, so color and shape. So you always play with numbers. Of course, you always normalize these things. Like you do some pre-processing, so you bring up it like in from -1 to 1 or 0 to 1 or some other thing. So, but let's say we are just playing with the raw data. And then you want this. Now the idea is how to discriminate this thing. What can be the best machine learning model for this?
maybe a line for this one. A simple line will do.
Simple line, right? You just draw the line and you think of it that anything above the line,
Will be banana.
anything below the line is the other one.
Yeah.
Now forget about bananas and apples. You can do a lot more complicated things with this. Human audio identification, face recognition, face verification, any kind of classification for two classes with just a line. Now we forgot this thing, we skipped this thing, but basically there are two types of machine learning things, like in the very broad sense. Supervised, unsupervised, and classification and regression. So what is
Start with
supervised?
supervised and
What is
unsupervised.
supervised?
Supervised.
The same
you
as
know-
supervised.
This is
know-
supervised.
Yeah.
In supervised, you have a data feature vector
And you know the level.
and you know the level. And you tell the machine during the training that, okay, this thing 1.5 and 3.5, this thing from here to here,
It gives one.
this is one. Or this is this guy, or whatever the level
This is supervised.
This is
Yeah.
supervised when you have this level. There is one more method, which is unsupervised. And unsupervised, you don't have these things.
So unsupervised goes for classification,
No, clustering.
Class.
clustering.
Yeah.
What's the
I will
difference
explain.
between?
So let's say you have,
The difference is that your objectives are actually limited here. You know you have bananas and you know you have apples. But for clustering, you just have a lot of
Things and you want
vegetables,
to-
and you need the machine to understand the differences and keep them
I
apart
see.
itself.
But
As
classification,
bananas, as
you have
apples,
the
and
label.
everything.
But in classification, you have the label, but you want like,
Exactly.
to-
So-
Classification, you know there are either apples or bananas.
so now let's say if we didn't have labels here, there was no ones and zero.
Exactly.
You see, no ones and zero, and I plot them like this. So everything is like this. You see the point? But we don't know what is this dot, what is this dot. But you can clearly see that there is one kind of cluster coming up here and something is coming here. And there are k-means, I will not go into that detail, but you can like initialize one center and assign the nearest ones and then redo the day. You can do like clustering like that's a very basic algorithm. And then this will be assigned random level that it will think that, okay, this thing is different from this thing. That's it. So it will not tell you the exact labels because you don't know, but it will at least tell you that, okay, these things are similar and these things are similar to each other in nature. So it will not tell you that this was label 1 and this was label 0 or vice versa, or banana and apple or humans and animals or whatever. But it will tell you that, okay, something here in this part are all something close to each other, and these guys, they are close to each other, and these guys are different from each other, and that is called unsupervised. Now, what was regression?
Well, I think the difference is that here we have separate spaces, but in regression we are trying to estimate something between these dots. For example, we have so many observations for maybe features of apples and bananas, not apples, some bananas. For example, the price of housing. We have some
That's a very good
features,
classical
something
example.
like
Yes.
I don't know, the number of bedrooms,
Yes.
the area of the house,
Yes.
something like that, and we are trying to estimate the number of another house based off these observations.
The price
and
of
based
the house based on.
Yes, so that's,
Yes.
that's a very classical example.
We try to fit a linear model into.
Exactly. So the point is, in classification, you always have a limited number of categories. Like you have apple, banana, oranges, tangerines, chairs, this and this. In regression, you want to find out or map something to a real value in the range of value, like let's say infinite numbers in this range. Like for example, this prediction of price. So prediction of price, let's say from a range of 0 to 1,000 euros. So you give some labels that, okay, this house is in this area, this home is in this area, it has this much bedrooms, it was built in 1965, and what else? So it is carpeted, it has nice things, like these are the features. And then you say, okay, it has 1k euro price. Then one more guy, it has 1.5 euro k price. So you see, like they are not exact categories, they are like real valued numbers. Of course, you can convert this regression to categories as well, like convert regression to classification by assigning that, okay, from 0 to this range is 1, from this to this range is another one. So how will you do this thing? So for example, we will consider now, like again, the two things, the two variables, the two features.
Two-dimensional
Yes.
space, right?
So let's say
You need one feature in order to present it in 2D, a feature,
Yes,
and
for-
then your value, the price and.
yes, I agree. So let's say the built,
the area of the house,
the built, the year.
construction year.
Yeah, so let's say if it was built in 1999, this was the price. If it was built in 2001, this was the price. If it was built in 2005, this was the price, and so on. Not like this, maybe a little bit like this. So if somebody asks me what would be the price if it was built in 2004, it's not a category, it's predicting some value. So I will fit this line and okay. But then there are techniques like how you find this best line. And then you say, okay, for 2001, this was the point, so for 2004, okay, this was the value. That's it, you just fit a curve. Now, we should not miss any points here.
But not all the problems could have a linear solution, I think.
Of course, no.
Yes.
I will explain that. We are coming to that next. Should I explain KNN?
Before going to KNN and going through algorithm, I still didn't understand the difference between clustering and classification,
I will explain again.
and supervised and unsupervised.
So, I will explain.
And like, which one goes with?
Did you understand the feature vector, right?
Yeah, I understood.
Did you understand the label?
Yeah.
Okay. Let's say I have this feature vector. One only with 2 points. Let's say I have 5 feature vectors, okay? Let's say this is A, this is B. Feature A, feature B, okay? No labels. And this is 0.5, 1, 0.6, 1.5, and this is 1.2 and 1.5, and this is 1.3, 1.6, this is 1.4 and 1.7. Okay, let's plot this. Do we have labels?
No.
No. So just believe this, that this is unsupervised. You don't have labels, okay? And let's plot this now in this graph. Let's say this is our x-axis, this is y-axis. So 0.5 and 1. Let's say this is 0.5 and this is 1. 1 point here. We don't know the label, so I'm just plotting it dot. 0.6 and 1.5. So 0.6 and 1.5 maybe here. 1.2 and 1.5. 1.2 here and
No, that's 0.5.
here.
Yes.
Here. 1.3 and 1.5. Here. 1.4 and 1.7. Here. Now, without going into the details of the algorithm, what can you see from this thing?
Like two clusters or something.
Yes, what does it mean? That these 3 points,
Label the same thing. Or...
they are similar to each other.
Yeah.
Because they are close to each other and these two are close to each other. And you just think that, okay, these 3 guys, these last 3 guys, they are 1, 1, 1, like some category, and the other guys are -1, -1, -1, or 1, 1, 1, 0, any levels but different. These 3 similar, these 3 similar.
Okay, this is unsupervised.
This is unsupervised. And you find these clusters. And what happened in supervised? You have the labels.
So it's like clustering supervised.
In supervised, you find this line and then you do the discrimination. In clustering, of course, you can also do like can and go, which one is clear, but you don't know the label. You just know that, okay, these are similar and these are different to each other.
In supervised, you know the label.
In supervised, you know. In unsupervised, you don't know.
Yeah.
But in unsupervised, you just only know that this thing belongs to this cluster. It is different from that cluster.
So what's the difference between clustering and supervised?
And maybe some application-specific examples would make it better. For example, think of your own problems. I don't know what exactly it is, but maybe you have some features, you have some observations from some cells, and consider that you are trying to distinguish some kind of disease. You are going to observe some features and try to understand if it is some meningitis problem or it is not. Okay, so that is not clustering. What was the other?
This is
Classification.
unsupervised.
You are trying to
Yeah.
classify between, for example, meningitis and some other bacteria. Now consider that you have some other problems. You have a lot of cells and you are supposed to just observe them and try to distinguish between different ones. So you have to just observe that part and see the different ones that share the same feature. So you can say that, okay, these are, I don't know
Similar
what the
feature.
hell these are, but they seem like some kind of same feature, same
Yeah, it's
cells, and these look like some kind of same
So
cells.
in supervised,
This is clustering.
in supervised you have the labels. In unsupervised you don't have the labels.
Yeah, that's
it.
fine. But between clustering and supervised,
There is no clustering is unsupervised
clustering is unsupervised.
Yes.
All right.
because you don't have the labels. The clustering is just an example of unsupervised learning.
Mhm.
Exactly.
Like you don't have the labels, so you do clustering.
Anything that is not clustering and it is unsupervised? Do you have any kind of other
I don't have an example in mind right now. That
It's
matches.
it's fine.
Object
It's fine.
segmentation in images, for example.
segmentation can be looked as clustering too?
Probably. But we
Alright.
can talk this in detail again as well.
Okay.
Yes. Okay. What's the time? I think we should be a bit fast.
Oh, it's fine.
Half
It's been
hour is
half an
gone.
hour.
So what is neural network? What is perceptron?
Perceptron? I don't know the exact meaning.
Perceptron. How to write it?
Perceptron.
Just write it on the board. Maybe Yuri knows what's perceptron.
You know.
Yeah. Okay. Come on.
So let's think of. Okay, so neural networks, they are inspired from biological neurons, and one single unit of a neural network is called perceptron or
So
neuron.
one-
Each one of those nodes are
Yeah.
perceptron?
Yes.
Uh-huh.
Like no.
So what is this? So it takes some input values, sum them up with some weights like weighted sum, and this is wrong, and pass it through some function, it will give you some output.
And is the perceptron different from the neuron?
No,
No.
They're the same.
Yeah.
That's the two
Well,
things.
I think one is like neuron is I
Yeah,
think
it's
the biological,
related,
and
yeah.
perceptron is
It's
like
machine learning.
machine learning.
Uh-huh.
Uh,
The
the-
artificial one is
It's just like one is biological and one is an animal.
Perception.
okay.
And when you combine these perceptrons, it gives you neural networks. So you have an input, it's coming, you have weighted sums like weight. You sum all of them, you pass it through some function, normally sigmoid or step function or some function, you get the output. And this whole process is done in one neuron.
And the difference between deep learning and machine learning?
I will explain.
Not yet.
Machine learning is the whole
Yeah.
big studies. In machine learning, you have supervised, unsupervised, neural networks, SVM, a lot of models, Bayesian. This whole thing is like coming inside. Neural network is just one kind of modeling of this whole data. And I will explain what's the difference between neural networks and deep neural networks. And the basic unit of neural network is this thing. So when you have a lot of them in parallel, I think we should remove this one.
Wait for the camera.
Let's say we have three features, okay? Do you remember like volume, weight, some other things? You give each of them as an input.
Wait, something?
This is like your feature input.
For apple and banana.
You see? Whatever, man. Some connections, okay? So this is your input layer where you feed the features or the data. This is your hidden layer where this gets some information from the previous summit, sigmoid, and blah 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 and whatever. It goes here, and here you give some output. I will not go into a technical detail, but this is like the basic neural network that you have neurons connected and you give the input and get the output, and of course then you like back propagate that, okay, adjust the weights because during the training you know that what was the real output, so you change the weights and it gives you like the probabilities that, okay, the sum of this one should be, let's say, 1, so let's say this is 0.8 and this is 0.2 as the output, so you think that, okay, this was for 1 and this was for 0, so this is more than this, so I assign it as a banana or apple or like what was 1. What makes a neural network deep?
Many layers.
Yes, when you have more than one hidden layer, it's a deep neural network.
Really?
Yes, there's no difference. Of course, some people might disagree that, okay, no, but what I was taught in my machine learning course is that when you have more than one hidden layer,
It's deep.
it's deep. But of course, now there are like many deep neural networks with the different architectures. How is this connection made and what kind of operation should be done? And it's like a lot of more studies, but we are not going to detail.
Does it make any difference philosophically? Between the deep learning and shallow learning?
Yes, I will explain why we needed deep learning. We are coming to that. Yes. Now, think of this neural network as drawing these lines or hyperplanes. Okay? And now we will explain. But then there is like convolution and this operations and what's like the function, how is the connection made, and the topology, like how you make this connection, and this makes like the whole deep learning a big research area that you can study yourself. Okay, now I think there is one phrase that I want to talk about. This is called curse of dimensionality.
Oh,
Curse of dimensionality.
Yes,
Yeah.
this is something that in machine learning you want to have less dimensions
Because of that, you're calling it curse.
because it increases the complexity of the algorithm. So and that's what we discussed in the very beginning, that for example when I have redundant features, I always want to get rid of this.
That's the same. That's the only reason.
Yes, because a lot of dimensions is not good. For example, I will give you an example, and I was reading somewhere this very basic example. So let's say there is this guy or girl, and he or she wants to find their best chocolate in a truck full of chocolates. But what's the feature of the best chocolate? Let's say this guy or girl has 3 features in the mind. That the wrapper should be green in color, the weight should be this, and the brand should be this. So she can just look for these and find out. But let's say if there are a lot of things, then what will happen? She has to search for a lot more because they're not discriminative enough, and she has to like see, it's like more hectic job. So increasing the dimensions means you have to do more computation. You have to compare and search for a lot of things. Like for example, in this case, when it was like this and this, so you are just comparing like, okay, this is the price, this is the this, and we are sure you find this. When it's one more, and one more, and one more, then you have to like compare many things.
But is it the same? Is it the only reason that we try to reduce the dimension, or irrelevant variables or features actually can affect the decision?
They both, yeah, because the complexity and also like there are
accuracy will be.
Of course, yes, like it's possible. I mean, in some cases it might not be. It might be possible that you need more discriminative features, but too many dimensions will be too complex for the algorithm to compute.
You
So
should
it's
be
like
more nonlinear to capture.
so it's like a kind of this trade-off,
Yeah.
trade-off, like what you
What
want.
you're doing in optimization, so then
Yes.
Sure.
So this was the term that I wanted to let you guys know, and then there is one more term, and that will explain why we need deep learning and why we should go from some other thing. We will see. There was this term, we called it VC dimensions. VC dimension. So what is VC dimension? Have you heard of this term before?
What is VC?
So VC was the name of this guy, Vladimir something, who also invented this SVM, I think.
Yeah.
He was the co-founder of SVM. Yes, so this term means that the maximum points which a line can shatter in all its possible combinations. And I will explain in a minute what does it mean. So let's say you have two levels, okay? So let's say this is level 1 and this is level 2.
The number of lines.
No. So, and I have only one line, single line, like this line. So how many points this line can shatter by considering all the possible combinations of this? Shatter mean like
Three.
separate.
3, no?
I will explain. Think about this. I don't know if I have the. No, I don't have the thing for this, but we can talk about this. So, for example,
5.
this line can shatter maximum of 3 points. For example,
Oh, you know the labels. Okay.
yeah. Let's say all the and for VC dimension, I mentioned something, all the possible combinations. Let's say I put it here. It can still shatter like this. Forget about this line. Let's say another combination of these 3 points can be just put this thing anywhere, like here. It cannot shatter. So there is one assumption with this VC dimension, that the points should not be collinear. They cannot lie in the same line. Now they are in the same line.
Yeah.
So with this assumption that these points should not lie on the same line, and the maximum points that a line can shatter for all the possible combinations of these points is the VC dimension of that line. In this case, I will call this line a model. Does it make sense or not?
A model.
Because this line is a model, it's a discriminator, like
Yeah.
we discussed
Yeah,
here.
yeah. Yes.
You see? So what's the VC dimension of line?
1.
3.
Wow.
Because it can shatter these 3 points. So let's say I have 3 points. This, this. Okay? Put these 3 points in any order except except that they should not be on the same
Yeah,
line, like
yeah.
this, and this line can separate it. Can you come up with some combination of these 3 points which this line cannot shatter except this line?
No.
No. Did you understand?
Yes, yes.
So the VC dimension of this line is
3.
3. Now imagine what happens at 4. Let's say I introduce one more point like this. Can this line shatter all the possible combination of these 4 points? No. Okay, it can shatter this. Good job.
But if you would put it up, it won't be.
It can shatter this.
No.
No. And what is this thing called? The famous XOR problem. XOR problem. So what is XOR problem? I think I have this. So let's say 0, 0, 0, 1, 1, 0, 1, 1. And what is the output of this XOR gate? It's like
0,
0, 1, 1, 0, right? This is XOR gate, right?
Yeah.
How can we plot this XOR gate? So for 0, 0, it's 0. Let's call the 0 with the 0. So this is 0, okay? 0, 1, 0, and 1 is?
No, that's 1, 1.
That's
Sorry.
1, 1. It's 0 there.
You just plotted 1, 1. and
Yes,
not 1, 0.
on the
It's
axis,
supposed to be
just.
the exclusive OR.
Yes, XOR.
Fahad, put
This
it
is
like.
XOR, right?
Yeah,
Yes, I mean
Yes.
in your plot you put it 1, 1. The point you.
0, 1, sorry. 0, 1 is 1 right here, right?
Yeah.
Is it true?
Yes, yes.
Yeah.
On the
1,
axis.
0 is 1.
Yes.
And 1, 1 is?
0.
1, 1 is like this, right?
Yeah.
The famous XOR problem. Can this line shatter this?
No.
Now what do we need here?
2 lines.
Something nonlinear.
2 lines. And these 2 lines come from which part? Deep learning.
Yes.
More layers.
Great.
This guy Hinton, I think it was Hinton idea.
Yeah.
Yeah?
Yeah.
The XOR example also.
Yeah.
was this example.
Is it also his example?
Yeah.
So he thinks that okay, if we, because people were stuck that okay, deep learning is vanished. No, neural networks is vanished because it cannot solve this problem. Because neural networks also technically kind of draws the lines. So the research is gone for years and years. But this guy, he said like okay, why not draw 2 lines? 1 line here, 1 line here. Anything above this line and below line is one class, and anything between these lines is another class. Smart.
He's
And which where was this?
2000, 1999
1999.
or 2000? I don't know. We should check.
I guess it's 2002.
2002.
Yeah.
Like
I'm not
around
sure,
this
but
area
Yeah.
when the deep learning got a boom. That okay,
Yeah.
man, it can do wonders. Deep learning. Now we have deep learning. Let's go back to our SVM. Now the point is, are we running out of time?
Why? Why are you in rush? When should you
Lots of
leave?
ground to
Weekend,
cover.
man.
Ah, sorry.
VC dimension is done. SVM. Let's talk a little bit about SVM, okay?
All right.
Let's say we have this line which is doing this nice job. You all know basics of SVM. Maybe we can have a next session of just SVM, but I will just give a brief overview.
Yes.
What SVM does is, it only works with lines. It tries to find the hyperplane or hyperplane or line and try to find these points. But the problem is, what will happen if we have a data like this?
More than one.
We should have something
Hyperplane,
nonlinear.
no?
So the kernel tricks are thing.
That's the point.
You should find what?
So then there is something called kernel trick, and in kernel trick, let's say this is the kernel trick, some function or some magic box or kernel function or whatever you call it, like okay, I don't know, whatever. You pass this data to this thing,
Transformation, you can say.
to higher dimensions, much more higher dimension normally, and in that feature space, it will, I don't want to draw it in like 3D or something, but they will be like like can be separated in the line.
Yeah.
Mhm.
So you do all the magical things in this. After passing this to this thing, you draw the line and you transform back from here to here. And when you transform the points of this line here from this phase as well, actually it's line there. SVM still works with line, but when you draw it here, it's something like this.
I think the best example for this is the x, y coordinate to the polar coordinate.
Yeah.
This.
That's the magic.
Mhm.
So now you know SVM.
Yeah.
For using SVM, MATLAB has a directory, not directory, library, but I prefer using libsvm.
libsvm.
So libsvm is good. I prefer libsvm. So if you want to work with this, and libsvm is a lot of like there is
Yeah.
SVR, support vector regression, one class
But in
SVM.
libsvm there are some problems sometimes with some kernels.
Uh-huh.
Yeah, with some kernels it does not function.
libsvm.
Before I was using this.
libsvm has this problem for MATLAB.
libsvm.
Okay, now let's talk about what? We are done with a lot of things. Okay. Overfitting. How many of you know overfitting?
Overfitting. Yeah, overfitting and three kind of fitting, I think. Over and
Underfitting, but
Underfitting.
overfitting is like more popular.
yeah.
Okay. So overfitting is, let's say you have this kind of data. Okay. 0 is one class, the other one is another class. What will I do now? The ideal is that I do something like this, that okay, I draw a line like this, go 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 like this. What's the error?
This is perfect unless it cannot be generalized to
Yeah.
the new observation.
And that's the overfitting.
Exactly.
You see the point? So
Too perfectly generalized. as you
yes, and that's what we call overfitting. That okay, it's good during the training, like okay, it's doing a great job. But when you put it to the test in real time, no, you cannot do that. So you want it to be something like this. So of course it will give you little bit of error during the training because you misclassified this one, but you can generalize and put in test in real time. So now you know overfitting. Okay, that's good. Okay, little bit about making the experimental setup, cross-fault validation, and accuracy measurements, and then we can just stop. Okay?
We can start the weekend.
Sorry.
We can start the weekend. We
Yeah.
can start the weekend.
Yeah.
Already dreaming.
So, do you remember, like in the beginning, what was here?
Features, labels, and all of this. And sense.
Some feature, some label. Okay. How you make the system learn the parameters? Because when you have this machine learning model like SVM or neural network or some other things, you have a lot of parameters, and you want to avoid overfitting. How to make the model? How to fine tune it? So you do cross validation. In cross validation, you try to make k sets, let's say 5 sets or 10 sets of this data. Split it, right? Then split it in equal proportion. So let's say if you have 3 classes, so you always have the equal percentage in each set.
Now, how do you know this?
Let's say if I have like 50% from label 1 and 25% label 2 and 25% label 3. So you find these k sets or 5 sets like or 10 sets, whatever, like 10-fold cross validation if you want to do. So in every set you should have 50%, like in this whole one set. 50% should be from 1, 25, 2, like you always keep the record the same in these subsets. And then what you do is you train your model with 10 minus 1 or n minus 1 or k minus 1, whatever is your sets. And then you test on the other one. And you repeat the same process until and till all the sets are once in test
Test.
set. And of course, then every set will be in a training, and they will have this combination. What?
Once you have your data set, how do you find the best model for your?
Yeah, parameters, right? There is no best model in machine learning. There is always like this thing will work nicely for this problem. This will work nicely for this. This will work nicely for.
Assumptions.
What assumptions?
Assumptions.
Like assumptions.
Assumptions for what?
Assumptions. Like you
To
predict
assume
kind
something.
of. Yeah.
Yeah, I know the word, but what do you want by assumptions?
Like you mean like for example you say maybe this problem goes better with SVM or like that.
There are some basic rules. Like for example, supervised, unsupervised, one-class classification, neural network. So neural networks works nicely when you don't have the features.
Neural
So-
network.
It creates the feature.
So you have a raw data. Like for example, I
You have
have
missing features, you mean?
No, not missing features. So for example, when we talked about this, that this is apple and this is orange, okay? So first we were talking about what? We were talking about that, okay, we have weight, we have this, but imagine I want to do the classification by just looking into this apple and banana. And let's assume that I don't have the information right now, that I cannot really think of it, that okay, should color or these things be a features or not. So I will just feed the raw